Okay, let's unpack this. We're doing a deep dive into the world of structural health monitoring, SHM. We're talking about those really critical systems, huge wind turbines, but especially aircraft.
Right.
And the threat isn't some big, obvious failure. It's the subtle stuff. Micro cracks, maybe some premature delamination, and it's happening in flight.
In service, yes.
So the big question is, how on earth do you detect that while the plane is flying with these tiny little sensors, the PWAS, without adding a bunch of weight?
That is precisely the mission here. We're looking at a system that fuses, hard physics-guided Lamb waves with machine learning.
Okay.
But what really makes this interesting, I think, is the focus on quantifying uncertainty. It's not just a yes or no on damage. It tells you how confident it is.
And that need for confidence, it comes from some of the basic rules of SHM, right? The axioms. We don't have to list them all, but what's the core challenge this approach is really built for?
It's all about variability. One of the axioms is that your feature sensitivity, how well you can see the damage, is always tangled up with environmental changes.
So a perfect reading in a cozy lab doesn't mean much when you're at 30,000 feet and it's freezing cold.
Exactly. So this system had to be built from the ground up to handle that messiness and actually prove it's reliable.
So to prove the concept, the sources talk about a lab setup, a small aluminum plate, right, with a PWAS actuator in the center.
Yep, a simple proof of concept.
And the damage was just sticking a small weight on it, the 16-gram or 32-gram mass. So how does a tiny weight like that actually mess with the waves? What are we even tracking?
So you're tracking the S0 and A modes. The S0 is a faster sort of compressional wave, and the A0 is a slower bending wave.
Okay.
When you add that mass, you're locally increasing the inertia. It stiffens that one spot, and that little change scatters the wave energy. It attenuates it.
So the signal gets weaker.
Right. The first, most obvious feature was the envelope magnitude. The bigger the mass, so 32 grams, the lower the wave amplitude. A pretty linear effect.
But that sounds, separating 16 grams from 32 grams just based on that, it must be really tough, right? They're pretty close in size.
You've hit the nail on the head. That's the problem. The linear features, they showed a huge amount of overlap between the two damage levels.
So what did they do?
They had to look at something much more subtle. The second harmonic index, or SHI.
Second harmonic.
Yeah, so they excited the plate at 20 kilohertz, but when they measured the response, they saw a little spike of energy at 40 kilohertz, exactly double.
Wait, hold on. So the 20 kilohertz is the main note you're playing, and the 40 kilohertz is like a faint, high-pitched buzz, like something's rattling.
That's a perfect analogy. That 40 kilohertz signal is a classic signature of acoustic nonlinearity. It suggests there's microslip or some intermittent contact between the mass and the plate.
The bond isn't perfect.
The bond isn't perfectly linear. And adding that nonlinear insight, that SHI, was the key. It dramatically boosted the classifier's ability to tell 16 grams from 32 grams.
Okay, that's a huge step.
Mm.
But we're back to that variability problem, that recall increase that was still in a clean lab.
Yeah.
How do you make sure this works when the temperature changes or there's other noise?
And that's where the Monte Carlo procedure comes in.
Mm.
It's a really rigorous step. They basically stress-tested the signal itself in software.
How so?
For every single waveform they measured, they generated 5,000 synthetic copies. But on each copy, they added random noise, they tweaked the amplitude by, say, plus or minus 5%, shifted the timing a little.
So you're basically simulating what happens when that plane flies from a cold Alaska runway to a hot Arizona desert.
Right.
But you're doing it thousands of times to build up a statistical picture of reliability.
Precisely. It's metrological best practice. By doing that, you're not just getting a single answer, you're getting 95% prediction bands, you're getting a calibrated decision score. It's a real confidence rating.
So you feed all that data, the real and the synthetic, into the machine learning models. What came out on top?
The ensemble methods.
So a committee of algorithms works better than one specialist.
In this case, yes. AdaBoost M2 had the best overall performance, about 85.7% accuracy. It was great at telling a healthy structure from a damaged one.
But I sense a but.
But, and this is the crucial part, the study confirmed that even with that clever SHI feature, the probability distributions for 16 grams and 32 grams still overlapped by about 30%.
So it quantifies the remaining confusion. It tells you exactly how hard it is to tell two similar damage states apart.
Exactly. It confirms that distinguishing between closely related severity levels is still the hardest problem in SHM.
So wrapping this up, what's the big takeaway? This whole pipeline, this transparent uncertainty-aware method, it feels like a really crucial step towards SHM systems that regulators can actually trust.
Absolutely, because they can see the error bounds. But for the listener, here's a final thought. This was a fantastic proof of concept with mass loading. The next great step, the one needed for real aerospace certification, is to take on service representative damage. We're talking through cracks, delaminations, fretting fasteners, and you have to do it all while running environmental sweeps, especially temperature, to truly prove out that probability of detection. That's the final frontier here.